record. Okay, welcome to the last session of our artificial, what is this? AI, artificial, what is this now? Artificial intelligence and machine learning for engineers. Okay. And we are doing the last topic of this course, the artificial neural network. And we are going to the last stretch of the example for the semester. So this one will be our last meeting, and we went through this example before. The only problem was the internet suddenly went off, so we have to stop. Okay, so we are given. Let's just go back to this example just to recap before we proceed. So this was an example of the XOR, exclusive OR, Boolean, what is this? Boolean mathematics. To say that if there are two inputs, X1 and X2, there is a corresponding exclusive OR output that is only true if one of the inputs is true. Okay. If one of the input is true and the other is false, okay, that's the condition. If both inputs are true, the output is 0. If both inputs are false, the output is 0. Okay, so this is the classic example of the perceptron model of the artificial neural network, the single layer perceptron, where it was not able to classify or to output the correct, the expected output for this kind of inputs. So now, because of that, many of the artificial neural network papers before were recalled, and they have to publications were being recalled because of this particular fault or some bug or whatever. You can say it a bug or some mistake in a model that it cannot solve this simple problem. So now the basic solution to this is that you increase the number of layers. So now we have, instead of just one input layer and one output layer, you include one hidden layer. Then it becomes solvable. Yeah, and so on, and then it continues on nowadays to much more complicated problems. The more you include the number of hidden layers in the artificial neural network, some problems that were not previously solved can now be some sort of solved at an acceptable level. So that's the motivation for the deep neural network. You just constantly increase up to a certain level, to number of layers of hidden layers of the artificial neural network to solve a particular problem. Okay, so we already discussed all these equations such that we have in this case here inputs, the inputs from the table x1 and x2, and it outputs z1 and z2. Okay, and in this layer, in the input layer, and in the hidden layer, we have inputs of z1 and z2 that will output the final output of of this model. Okay, so what we need to know now is that we are discussing a backpropagation method where you update the weights in this. We'll initialize the weights and update the outputs. And then once you get the output, so this is feed forward computation where you have given all the x1 and x2, I mean the x values, you have the output, you have the v1 weights and the v2 weights. So we are saying here that, let me do again. Okay, that's our input. And so we have, okay, just to make sure that this is our v. Okay, our weights are called v. So here we have v1 0. Okay, here you have v1 1. Okay, that is the weights where your output is z1. Okay, And here is the V for this one is V1, 2. Okay. So the other one is the output V2. So here, this is your V1. V1, so that is V1, okay, transpose multiplied by X1, X2, which is your input. Okay. Okay. This part here. Okay. And now your V2 is here. The output, so here you also have, that's V20, that's the bias. So here, this is your V21, and this is your V22. I think they initialize everything to 1. So the weights is 1 here, and the weight here, that is the weight, and that is also weight 1, and that's a 1. Okay. Then that's how we got here V2. So that means that V2 again transpose multiplied by X1 and X2. Just want to recap so we can discuss again in smoothly. And so now when you have weights here, so your input here, okay, again, this is Z now, this is Z, the input is Z. So you have, in this case here, you have W weight of 1, 1, okay, weight 1, 2, and this is your bias weight 1, 0. Okay. Okay, so now again, this is W1 transpose of multiplied by your, okay, Z1, Z2, sorry, there is a bias. So this one is 1. The same thing here, this should be a 1. That's for the bias, and that's the 1 there. Okay. If you start with V10 like that, so the 1 should be here. Okay. You understand? I mean, it's just a matter of putting the 1 wherever your corresponding weights are. Okay. So in this case, feed forward, I think there's no question. Okay. We are okay with that. Okay. We are able to compute the outputs for the input layer. The output are Z1 and Z2. And then for the output layer, now you have the output Y1 and you have inputs Z1, I mean Z0, Z1, and Z2. Okay, and that is your output Y1. Now we go to the feed forward process. The feed forward process is to update your weights. Yeah, to update your weights so that you first update your weights here, the W's, and then once you update your weights, you use that update of weights to update now. After that, you will be able to update, after updating the weights, then you will now have using those weights that you previously computed of the updated weights of W's. Now you can update the weights of the V's. Okay, and then after you updated the W's and the V's, then we'll update they will feed forward again and update back propagation. Okay, so I hope that is clear. So now I think we discussed this one already before. Okay, so this is this is just what I mentioned, and these are the initial values of your V's. V0, V10 is 0.01. No, this is not. It is just the convention. So X1, X2. So this is what we say. So V11, V10, and V12. Okay. So don't get yourself confused. And then V2, we output of V2. So this is V21, okay, V20, V21, and V22. Okay. Anyway, so let's continue. So this is the initialization of the weights now. So the initial values of the weights are this. We randomly assign. Okay. And now we feed forward. We compute. So when we feed forward, we computed already this one before. Your Z in is just this V times V1 times X, which is this value. Okay, V1 times whatever your X1, X2, and V0. In this case, this is your V1 output. Okay, now we use then we use this Z in, where you have Z in to come out with Z1, Z in 1, and then for Z2 you have Z in 2. Okay, so anyway, we discussed that one already, and in our feed forward process, we see that the output is not zero. So because we initialize our inputs to be, I think we choose the input to be 1 1. I think this is the input 1 1 that we use. Okay, and you see the input 1, this is 0.3. Okay, V10. The input is all 0 0 0 0. Yeah, sorry. So that means that we use the first, this one, we use the first input x1 and x2 to be 0. The output should be 0. So when we do that, we're using the initial values of our weights, and then we compute here, just substitute, then the output should be 0, but the output is 0.42. Okay, so in this case here, we say that if the output is less than 0.5, then we can say that the output is, this this is not, it's not 0.5, it should be 0 and 1. Okay, so now if you output 0, this is not 0, this is greater than 0. Okay, so now, let's continue with the computation. So now this is how we assign values for your V1 and your V2. So we start with the 0, V0. So that means your X inputs also will be starting with 1 here. So if you multiply this one with X, so it will be X1, so 1, and then X1 and X2. Okay, so that, I hope that is clear. The same thing here. Okay, and the same thing here, because that's Y0, so that means that 1, then Z0, Z1 and Z2. Okay, so that's how you compute. Okay, now because these are our initial values, and then we compute, so we just substitute. So your V10, this is the bias, times input X1 and X2. So your input X1 and X2 are all both 0, and that's 0. So this is how you compute your Z1. So the values of Z1 is computed. The next, the same thing, your Z2. So this is the bias times X1 and X2, and they're all 0. So you just substitute 0.56. That is your Z2. So now, in this case, so you compute Z1 and Z2. So this is your Z0. So this is your Z1, and this is your Z2. Okay, so again, we compute this to be and then it becomes negative, and you plug it in here. So now it becomes positive. So your output is 0.42. That is not 0. Now, we only have one output layer, that is k is equal to 1. So all these are all 1. Okay, delta all 1. And so there's no summation that we previously described. We already discussed this last time, that here there is some summation term. Okay, this summation term does not apply because you only have 1k. So k is equal to 1, and so these, we can remove the summation, and then everything else will be the same. Okay, so let's continue. So now let's go to backpropagation. So here you only have y1 output. This is your target value, and this y1 output. What is your target value? Okay, let's see. Let's go to the. I want to take the picture. Picture of the table, so we can easily grab it. Okay, there. So that's the. Okay, that is our table, and so our target value is 0. So now, we use the delta here, and so in this delta we substitute the delta k to here. Okay, minus z1. So that means this delta k, this whole thing becomes this one. Okay, so that should not be an issue. So now your yk, we know what's your yk, we know what's your yk output. This is just y1. This is just one, and then target value is 0, and so on. Okay, so that means that in order to update your W11, okay, there are two things that we need to update: W11 and W12 and W10. Okay, so here, let's continue. Oh. Here. Okay, so in this case here we have, okay, again I want to show this one. So we have your delta K, and that will be, okay, so this is just delta 1 because we only have K is equal to 1. So Y1, that is 0.42, that was previously computed from the feed forward, 1 minus, okay, 0.42, and the target is 0 because we are considering this. Target is 0 minus Y1, which is the output. Okay, it's a substitution. So delta 1, okay, your K is equal to 1. Okay, now, so this delta 1, if for the hidden layer, your delta J is, your J is equal to 1 and 2. Okay, so this is for the output layer, and for the hidden layer, you have a delta J1 and delta J2. Okay, so here your J is for Z1, okay, 1 minus Z1, delta K, where delta K is that delta 1. Okay, because this is doing feed back propagation now, and WK is equal to 1, so depending on the J, so K W11. Okay, so what is the W11 now? That is your just substitute, and this is your delta 1 of the hidden layer, and the delta 2 of the hidden layer J is equal to 2, so you have delta 1, which is that delta K, and W12, which is the current W. Okay, so here, and then multiplied by this is the W1, which is that this is the delta 1, which is that delta 1, and then your W12, which is 0.3. Is that that's my engineer. Okay, that's my meeting, the previous meeting this morning. So here we have so our let's just show our initial W's. So these are the values of our W's. Okay, it's just pure substitution. That's what I'm trying to say here. So here it's just you compute all the deltas, the delta 1 of the output layer, and the delta 1, delta 2 of the hidden layer. So now, so here, when you update your W's, okay, the W's of the previous of the output layer, now your K is equal to 1, and assume delta the alpha is equal to 1, and this delta WK is used here. Okay, this is not very efficient. So we update your W0 in terms of this. Okay, I should have computed this before we compute this. But anyway, so we update your W10 with this one, W10 plus the delta of W10. Okay, the same thing as W11, current W11 plus the delta of W11, W12 plus the delta of W12. So what are these? So we use the current values of our W1. Okay, let me just again picture the current W, so we will be convinced that they are the correct values. Okay, and then move to the next. No, this is my engineer. Move here, there. So now, so here, so this is the value of the weights. So now, I just want to show how this is being updated. So let's start from here. So the current values of W10 there. W10 is minus 0.04, W11 minus 0.2, and W12 is 0.3. Okay. So now our problem now is computing what are all these delta W's, delta W10, delta W11, delta W2, that will give us the new values of the W's. Okay. So now what is your delta W10? So it's here. I should have, this is not well placed, but anyway, so the W, okay, The delta W is this one, alpha times delta 1 of Z1, okay? Where in this case here, your delta K is 1, okay? Your Z, your J can be 0, 1, and 2, okay? So from the original equations, let's go here. Okay, so that we will convince ourselves that these are correct. So we update our W using this. Okay, let's start with that and then move on. There. So this is how we update our W. Okay. So to update our W, so the current W times, this is now the delta W10. So alpha times delta K times Z1, okay? So if this is delta K, K is 1 and then J is 0. So if we are doing this part here for K10, okay? So K10, so this is delta W of 10. So now this is delta 1 is just one value, times your Z0, that is equal to 1. Delta 1 is previously computed. That is the output of the delta 1 of your output layer, okay? So now, the delta 1, just substitute. The only difference here is you substitute based on the Z, okay? There's no changes here. So only the Z changed, the Z0, Z1, and Z2. Everything else is the same, okay? So now you can compute W10, W11, and W12, and then you update. Okay, so that's easy for updating the W's. Any questions? Okay, so to update the W's, you need to just compute the delta 1. Okay, please see here. You compute the delta 1, which is the delta 1 of our output layer, and then multiplied by your Z0, Z1, and Z2, depending on W10, W11, and W12, okay? So the delta 1 remains the same, only the Z changes that will correspond to your weights, okay? That's why in this case here, this is how we update it, okay? What I'm saying here, this is a different value, different from the original slide of where I adapted these slides, okay? So now, so this is, I think this is easy. So now we go to the updating the weights of the hidden layer, okay? So this is the weights of the output layer, and this is the weights of the hidden layer. Any questions?
I have a question.
Yeah, who's that? Introduce it.
In the slides, there is weights written different in those answers.
Weights that are written different.
Yeah.
Okay, let's see.
Where you're computing W.
Okay, which one?
The slide at the bottom.
Slide at the bottom.
Yeah. Where we are updating W.
This one. This one. Different. This one?
Yeah.
Yeah.
This is W11.
Mm-hmm.
The update of W11.
Yeah.
Let us go at the final answers on the graph.
Yeah. This one. No, after 500 iterations. This is after 500 iterations. We're only doing one iteration. We are only doing one. This is the final one, is the result, the weights that are updated after 500 iterations. That means you compute forward, backward. That's one iteration, forward, backward, another iteration, forward, backward. It's doing 500 updates of the W's.
I think the graph is on this slides that are upwards, not this one.
Okay. Not this one. This one? This one? This one?
Yeah, here.
Okay.
These are the updated values of
The
W,
first
right?
pass, yes, yes, that's right.
Why is W11 here different from the W11 that we found at the calculations?
Yes, that's why I put here, it's different. There's no rocket science here. It is just a computation of the delta. Okay, it's just a computation of delta 1, where delta 1 is one value multiplied by Z1. Okay, so here this is minus 0.43. So that's why I say that we have different results, because that is how it is just being computed. Okay, here you have to put alpha times delta 1, where delta 1 is the same for everyone. Delta 1 the same, minus 1.102, 0.102, that's all. All you are changing is the value of Z1, which is 0.43.
So I understand what you are saying. What I don't understand is that the updated W at the computation is not the same as the updated W that is shown on
Here.
Yes.
Yes.
Why? I just want to know if it's a mistake or
yes. That's why I don't want to say it's a mistake. I just say that our results are different. That's all. Because this is from the original from the originator of these graphs. So, but when I compute a different value. It is.
But they're supposed to be the same, sir, because they've used the same input as the one that you used, and all other updated Ws, I think.
Yes, Mr. Jayaslam. But I don't want to say it's a mistake. It is just different. Yeah, because there's no, okay, I also verified it many times, but there's no, I mean, it's just sometimes people commit mistakes, man, when you substitute. Okay. Okay, but as long as you know what you're doing. Okay. Okay. That's answer.
So I have a question.
Yes, yes. Aune.
I have confusion when it comes to initializing the initial values of X and Y, the data that we use when we compute for Z1. So if we get the same values after 5 iterations, if along the iterations, we change the initial values of X1, X2.
You have to go through that also. You have to correct the weights. It has to be true for all inputs, for all training inputs. You update the weights, you change the inputs. You can also change the input, change the inputs and see whether they are correctly classified. If they're not correctly classified, then you have to go through the updates again, updating the Ws because they're not correct. You just go through all these iterations. So because these values here that is shown, this one, okay, these are called your training data, okay. But of course, your training data, which can also be because this is all the inputs for this, there's no other inputs possible for the XOR. Yeah. But you can model it, you can test all the possible inputs in this case because it's known to you. Okay. So the same thing in other things that you're modeling. So you have to keep on changing the values for all the possible data that is given to you. Okay. For other data that you don't know, okay, once you're done the training, that means that for all the given inputs, you derive now the correct output. Your weights are correct because that's the idea of the training. Okay, you need to find what are the corresponding weights that will give you correct results for all the inputs that is given to you. Okay, so now, okay, in the case where there are other new inputs, then now you're confident that yes, whatever the result is, it is the correct classification.
Okay, but how do we determine that the updated values are of the right classification?
you check because you know the correct output, right?
Yes.
Yeah. That's why here you say, okay, maybe it's quite confusing. This one, this error term, this target value multiplied by the output. And then you correct the weights based on that error. As the error goes smaller and smaller, this is like the gradient descent method that we discussed. Once the error becomes smaller, here becomes 0, then the weights are, are correct. So you have to go through all the possible inputs, all the possible, all the possible input data that is given, all this data that is given to you. Keep on updating all those weights until the error, this error reduces. Then you're done. If there's still an error, you're not done. Okay? Sometimes it takes forever. If it takes forever, then it's not possible to have a solution. Okay? So we are doing all, the method are all exactly, the way that we did before. You check the error, and when the error reduces, then that's the time that your weights are correct. Okay? The only thing is the equations look different, but they are based on gradient descent method and some other methods to optimize. Okay, some other techniques that we apply. Okay. Okay. So should we continue? I think you understand already. So all of these are just pure substitution. So we move on to classify this, to classify, I mean, to update your V's now on the hidden layer, on the input layer. Okay. So now, okay, it will be dependent again on this delta V. Okay, your current V, then we correct it with a delta V value, VJI. Okay. So your J, your I, okay, goes from how your J, in this case here, J goes from 1 to 2, and then your I is just equal to, in this case here, okay. So you have J, okay, J from goes to 1 to 2. So if it's J1 and J2, okay, V1, because you have two outputs, V1 and V2, but you have yeah. So now you have okay. So now your I goes from what is the value of your I? Your I goes from 0, 1, and 2 because those are the components, and your Vj goes from 1 to 2. Okay. So here that means you have V1, okay, V1 0, V1 2, and V1 1 and V1 2. So these are your V1 0 depending on the J value. V1 0, V1 2, and V2 2. Okay. Now we are going to update it. Okay, based on your delta Vj. So your delta Vj is this. Okay, it is. I mean, I should change it in such a way that it will be just computed nicely like this. But it went through the author preferred to compute the delta V's up here. Okay, so here's the delta V's. Okay, delta V1, delta V2, and delta V3. Okay, so now just applying this equation. So your delta V1 0. So delta V1 0 is delta your J, whatever is your J. So delta 1, okay, your delta 1 and delta 2 for your J, and then your X becomes X0, X1, and X2. Okay, so now your delta 1 is computed up there. Okay, so all you need to do is know your delta. Okay, here. I don't like the way it is being, actually, honestly, I don't like the way everything is laid out. I should have, computed it in a more, just, I mean, it should not be going through all the deltas. I should want to compute all the W's first, and then the V's and their deltas. Anyway, so here, the delta 1 is computed here. So delta 1 is Z1, this one. All this, just substituting this one. Z1 times 1 minus K, whatever your input. So that means your J goes from 1 to 2. Yeah. So J1, so Z1 and Z2. And then multiplied by delta k, because your k is 1, so this one is nothing. So there's just delta 1 w1 k 1, whatever your j is. So they have w11 and w12 multiplied by later, because this is all your delta. The multiplication of the x is done later. Okay, so in this case here, the delta k, again, delta k is computed before, so no more here. This delta k is that. Okay, anyway, these are all purely substitutions. So this is, you know, this y. Okay, let's just concentrate here. This is your target value, this is the output, and k is equal to 1. That is your, okay, maybe make it bigger. This is your target output, this is your output, computed output. So everything is known, no more summation. So update whatever your k is here. The input is the x, okay? And then the output of that input layer, Z1 and Z2, and then that's it, finish. Okay, so it's just a little bit confusing here because it's done step by step. But then if you just do it in one pass like that, then it's more logical. But anyway, they compute the delta and then substitute it later, delta, and then substitute it to here. Okay, that's how they did it. And then the delta V first, the delta 1 and delta 2, and then you computed all the deltas already. There's delta 1 and delta 2, and then now it's the same thing. It is just based on delta 1 is constant, and then based on your input x0, x1, and x2. Same thing here, delta 2 is constant based on input x0, x1, and x2. You update your delta V's, okay? And then just purely substitution. This is your V's. Again, at one value, I find it different. Okay, so I just put different. Okay, and then this is your updated V's for one pass. And then that's it. After several iterations, this will be 500 iterations. This will be the final value. Any questions? Okay, all the equations are there, and I hope you do your, let me stop the share. I hope you do your exercise, because it's really, you don't really understand it by just looking at it. You have to really do the computation. Okay. And then if you want, please program. You can also program. Okay, run some simple programs and run several iterations and see if you can really, you know, you really compute the final, the same value as this, as in the lecture. Okay, just do one pass and then just continue for blah, 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 how many iterations. That's it. And then just like Hauni was saying, you also need to change the inputs, because it has to be true, not just for a for the input 0, 0, it should be also true for input 1, 0, input 0, 1, and input 1, 1, like that. Then this is a supervised learning. It will be just corrected based on whatever is the expected output. Okay. Okay, it's just like that. I mean, the whole process of machine learning, okay, is based on certain models. Okay, in this case, for A&M, it's a model of the brain. Okay, because of the model of the brain, there are ways that equations are being expressed. Okay, of the activation function and how the network is, the output are computed and the hidden layers, all these. And so, you know, it looks like the same, you know, similar to the tree. You know, you have like a root, and then you expand until you have a final decision. Okay, but in that tree there are leaves, there are several decisions there, and then in this case here you expand, and then suddenly you have an output like that. Okay, and a classification output. So yeah, based on the model, then you have different equations. Okay, but the principle is the same. It's about updates of weights. Okay. It doesn't matter what kind of weights you have, you initialize it and then update it eventually in order to classify the output based on the expected outputs. That's your training part. Okay, so the training normally finishes when you see the updated weights now classifies all at acceptable level, all possible outputs. Okay, that's when you know training is finished. Your model is correct now because your weights are correct. All of them can classify your training data, your given training data based on the expected outputs. Okay, I hope you find this machine learning class useful and with practical understanding. That's what I really want you to have. And then so that eventually you can also, I encourage you to run other algorithms yourself. There are many tools in the internet, and you can learn it yourself. Even my previous students that are now my graduate students, some of them are working abroad, some of them are graduate students abroad. I just teach them the basics, and then they keep on learning and then trying the tools online. That's it. I don't know everything. I just know the basics, and then I also know certain things based on what I need, and that's what it is. So you don't really need to know all the possible solutions, but you will be able to find. What I want you to do is you will be able to find an appropriate solution for a given problem. That's all. If you can do that, then what else you want? Okay. Jason, you have a question?
No, sir.
Okay. What if somebody from your village, Jason, will tell you, "Hey, I heard you learned about machine learning in your class, Jason. What can you tell me? Can you please tell me about it? How do machines learn?" Okay. Yes. In machine learning, so they say machines learn. So how? Can you tell me? Oh, I must be a very bad teacher, Jason. Okay. There's a basic information here. Yeah, it needs data. In the machine learning method, it needs data. Okay, data from actual experiment. Yeah. So if you have a data, you need the data. If you don't have a data, you cannot perform. Yeah. So you need the data. Yeah. So let's just concentrate on supervised machine learning. You need the data and then an output also based on that data. Okay. Now, for machines to learn, you have a certain model, and those models are based on the weights. That's all. Weights, coefficients for polynomials, weights for for anything, for decision trees, weights for artificial neural network, weights for SVM, like that. Yeah. So you update those weights. So weights are updated based on the error of the computed output against the expected output that is based on the experiment. So you keep on computing until the weights are, going towards the proper weights that will give you the least error. Once the error is small, then the weights are correct. Okay. Then now that's how machines learn. Now, given input, it will be able to give you the correct output because it was trained already. The weights were updated already. That's it. Maybe in the future there's another method of how machines learn, but for now, machines learn based on the weights, by the updated weights, that we give them an updated weights that will give us the least error from the expected output. Okay, so given new data, we assume our model is correct. Given new data, it will give us the output that we expect. Okay, Jason, can you say that in your own terms again one more time? Hey, Jason, I heard you already. You're taught by this wonderful professor, Professor Jamisola, on machine learning. I wish I was also his student. Can you tell me what is this machine learning? How do machines learn?
For machine to learn, there must be data, and then the models that have weights that must be updated.
Then, how do we know that they learn already?
How do we
know that the machine learned already?
I think I missed that part.
Oh, you missed that part. Okay. We know that the machine learned already. When given the input, they will spit out the expected output. Okay. That means your weights are the correct weights. They've been updated based on the training, because our training, okay, is based on minimizing the error of the output. Okay. If you spit out the correct output, then they learned already. Because
Okay,
that is what we want. Huh?
Okay, so we see that the machine is learning when it gives out the expected output, right?
Exactly.
And we can also say that the machine is not able to learn when it gives the wrong output.
Yes, that means the training was wrong. It didn't learn properly. Just like, when you grew up, you go to the wrong teacher, you're taught wrongly, so you didn't learn properly. That's what they say. Yeah. So you're guided by the right teacher, luckily with a wonder prof, to guide you in the correct direction, and then you learn well. Okay. Anything else? Okay. This is our last. Can you open everyone's camera so we can have a goodbye for the last time? Maybe we will see you in the final exams, just before the final exams, so you can see me and you will be inspired. Yeah. Remembering your wonderful prof that's preparing everything for you so that you learn. Hopefully. Mudise, where are you, Mudise?
Sir.
Okay, open your camera. Where is Chepo? Chepo, Masa, can you show your Lefa? Can you show your face?
Sir.
Yes. You have a question?
I have a question. I have a question regarding tomorrow's test.
Okay, what is it?
Which topics will be covered in the test?
The topic that we didn't have a test yet.
Okay, that's right.
From the test, from the topic after the long test one until now. Okay, I want some other lecturers would prefer to cut the topic, not give everyone in the final exams, not give all the topics. But no, I don't want that. I want all the topics covered in the test so that it will be like your practice for the final exams, because the final exams has a much higher percentage. Okay, so you need to have a practice in long test too. It doesn't matter if your long test is you have a low score, but you had the practice already. So eventually in the final exams, you will have a much better score. Okay, definitely. Mr. Modipilo, Propileng, you agree? You look scared.
Yes, sir.
Don't be scared. All you need to do is practice. Okay? Okay, come on. Let's give a round of applause to the wonderful prof who is giving you so much this semester. Come on. You don't agree? Come on. You see, I agree. 101%. Bright didn't agree. Okay, anyway, if you have any more questions for long test 2, you can still throw that in WhatsApp. Otherwise, if you have other questions in preparation of the final exams, no matter, maybe I travel somewhere, just throw it in the WhatsApp or email me. I will answer them. Okay? Okay. Okay. Thank you all and good luck for tomorrow. Camila will take over for tomorrow. Okay? Bye. Good luck.